Good morning. I am Krishna Kumar. Welcome to Krishna's Classroom. We begin with another episode of Riemann Stieltjes integral. Continue from where we left last time. Just recall what we did last was that the following result. That is, we assume, okay, what we have is this. F belongs to R alpha. These are the assumptions on AB. M less than or equal to F less than or equal to M, because it's a bounded function that we are considering. Phi is continuous. On MM, and Hx defined as phi composition, and then H belongs to this is what we proved last time. And in fact, we make a remark here. If we have phi discontinuous, but still phi R alpha, on phi is assumed to be Riemann integrable on the interval M to M, then H may not be we give an example. We take alpha x on the interval 0, 1. Now define, so let F be the popcorn function. So this Fx equal to 1 if x equal to 0, 1 by q if x belongs to where x is equal to p by q, with the condition that p the common divisor of P and Q is assumed to be 1, and this is equal to 0 if x belongs to 0, 1 is irrational. This is the function that we have. And we define phi x to be equal to 1 on 0. So this is a discontinuous function. Okay. So phi is discontinuous. But phi is Riemann integrable on and one can immediately show that is the direction function. Which is not Riemann. So even assuming both these functions are Riemann integrable does not assure us that the composition is Riemann integrable. That's an example which we have recalled earlier, but it may be worthwhile to look at. Now, what we want to work on is step functions. Okay. I was telling earlier that, so just we'll make some remarks. Now you see, alpha is a map from AB, which is monotonically increasing, but not necessarily continuous. Therefore, alpha is a map from AB to alpha B. But the problem with this map is if it is a continuous map, then this is an onto map. Otherwise not. If alpha is continuous, then it is onto. But otherwise, you cannot assure that it is continuous because the image is not necessarily an interval. For example, look at this function. So let us take a function, something like AB to be equal to -1. Take this interval. Then we take the function alpha equal to -1 for x belonging to -1, 0, something like 0 equal to 0 and +1 . So alpha is a map from -1 to 1 to -1 to. It has a discontinuous set. It is zero. Now, what is the image of this? Okay, so let us examine that. 1. So alpha -1 is -1. So it's a map from here to here. Alpha 1. But the range consists of nearly 3 points. This is 1, this is 1 and 0. So this whole part goes into this. This whole part goes to this and this goes to this. So the range is consists of simply 3 points, which is not an interval. Okay. So that's something very interesting about the introduction of alpha. Therefore, whenever you talk about Riemann integrability of a function defined on the interval -1 to +1 with respect to alpha, okay, right? So you have f defined on this interval and defined on this interval and so on. So you see that there is a, if you look at the graph of the function alpha is this. It is this one and this one. So -1, 1. This is the graph. And there is a jump discontinuity at the point 0. Okay, it is neither right continuous nor left continuous. And the image itself is not an interval. Okay, so that is one thing that we have to observe. So, if you were to introduce a partition here, say call this x0, x1, say this is 0, x2, x2, just a partition. So let us take the partition P. So this will induce a partition. What is the partition that it will induce on this? See that alpha x0, it is on the interval alpha x0, which is equal to -1, less than or equal to alpha x1, less than or equal to alpha x2, less than or equal to alpha x3 which is equal to plus 1. What you observe is that in this specific case, you see alpha x naught equal to alpha x1 which is less than alpha x2 because you are taking x2 which is equal to alpha x3. Okay, where we assume 1 0 belongs to the interval this is the assumption that we are making. Okay, so the partition consists of the image of these points will be consisting of this. Okay, so if you were to consider this on this set, now you see this set is no more an interval. Okay, so it consists of 3 distinct points -1, 0, and 1. Okay, and that is the point I want to make. So if you are defining a function on this and then go for the integration, so what happens is the presence of alpha takes the same values, and one can easily find out what is going to be. Suppose you are taking a function, what is going to be m f alpha f alpha upf alpha is what? upf alpha is going to be minus L. This is equal to essentially it is going to be what will be this? This is equal to supremum of f on x1 x2 minus infimum of on x1 multiplied by what? Alpha x1. Okay, and that's equal to, say, m by our notation, it is m1 minus m1 into alpha x2 minus alpha x1. Alpha x2 is minus 1, alpha x1 equal to, so it is 2. Okay, right? Now if you are considering a continuous function, you can make this small and make this arbitrarily small. That is possible by making m1 and m2 small. Okay, this can be made less than epsilon provided f has continuity. Then f has continuity at the point 0 becomes relevant. And in fact, what happens to f elsewhere is totally immaterial. Okay, so we observe that for f to be Riemann integrable with respect to with respect to alpha, it is essential that f is continuous at 0. Otherwise, you cannot make this UPF alpha minus LPF alpha arbitrarily small for any choice of the partition. Okay? Right. So, what more we can infer? What more we can infer is that the values f takes on -0 to -1 to and minus delta delta to 1 delta positive to the interface. That is because you see that alpha x is equal to alpha y for xy belonging to -1 to 0 and alpha x belonging to 0, 1. Therefore, the length that you attribute to the interval xy. So, whenever the interval xy, that means xy contained in the interval -1 to 0 or one alpha length 0. So this is the important part. See, on this portion, when f takes on these intervals is do not matter. What matters is f at 0 minus And once f is not continuous, they are going to be different. Okay, so there is a problem, right? That's why it does not become integral. Okay, so if they differ, that's the important thing. So something about this alpha. Okay, so as far as this portion is concerned, no interval has positive length. It is only zero length. Subinterval has to take x, y, then see the subinterval has only zero length. That's the one. Now that's a remark worth noting. Now we start working with what we call the discontinuous functions. So when we work with the discontinuous functions, let us see what discontinuous alpha. Let us see what is the consequence of that. In fact, you see that the most interesting thing is that your infinite series can be geared into the language of an integral. Okay? Right. So let us start. So we start looking at alpha given as a discontinuous step function. Okay, let's start. So let us take the identity function, the unit step function. Ix to be defined as 0 1 greater than 0. So that is this one. This is 1 and this is 0 here. This is the function. So I is now is this. It's a different color to display this. This is this one. That's the graph of the function. That's a unit function. Okay. Now we define the following function. So let us define for a less than s less than 2. And what is this function? Suppose this is a ix minus s is some point here, that's the point. Then you see the function that you have is alpha s is this one. This is that. This is your alpha s, alpha x. So we shall prove the following here. Assume that is bounded. Assume f is continuous at x equal to s, and then first let us prove it and then we shall make some comments on this. So what one does is maybe, so we take this stop, we isolate this point, and we introduce it. So we introduce a partition. So let P be now let us compute the, first we have to prove that f is Riemann integrable provided f is continuous, or under the given condition it is Riemann integrable. So what do you have to do to work out this? U, E, F, alpha minus alpha. This, a small computation will tell you that this is essentially this is M1, M2, okay. M2, the usual rotations. Okay, so this is M2 minus M2, where M2 equal to supremum of F over X2 X2 F. This is the increment over it. Now, if F is Riemann integrable, then of course, given an epsilon positive, there exists a partition such that this is less than epsilon. Now, you see, this is true for any partition taken in the form so that S lies between x1 and x2. Okay, so we are assuming S lies between x1 and x2. Right? Or even take S to be something like this, equal to isn't it? Okay. Then what happens? Now, given epsilon positive, provided now this is assured when F is assumed to be continuous at this point, because you can see if this is not true, you can always one can always choose x0 and x1. So if F is continuous, if this is possible, you are just using the continuity at the point S. You can find a delta such that given epsilon there exists a delta such that this is, so that works well. Okay. If it is not continuous, then what happens? Suppose it has a discontinuity. Then you see, suppose it has a discontinuity at S, then you have, in that case you have F S minus 0 minus F S plus 0, so this plus 0 minus F S minus 0 is strictly positive if not continuous. And you can even make it something like greater than, say, the absolute value of this can be made equal to, this is equal to is greater than some psi positive. That is possible. And therefore this cannot be made arbitrarily small. The consequence will be no matter how small an interval you choose. So no matter how small, if f is not continuous at S, then no matter how close one chooses, x2 and x3, such that okay. Okay. Therefore, you see that you cannot make this smaller than alpha. That's the problem. Okay. This cannot be made smaller than alpha. Therefore, the necessary and sufficient condition for Riemann integrability with respect to alpha will be right. So this is important. It's not continuous. I mean to say it's not continuous. So that's the conclusion. Okay, if f is continuous, then you can do it. If f is not continuous, it's zero. But what matters is, see, you can have f to satisfy any other condition except boundedness. It is sufficient to assume that. So yeah. Any A may be discontinuous on A, yes, and yes, B that it is bounded. The integral. So it doesn't matter what is there on the interval A to S and S to B. It's as though it is not there at all. So the contribution that comes from there, as long as this F is bounded there, the contribution that will come from there for any interval is going to be that it is alpha y minus alpha x, which is equal to 0. Okay, so to this difference, no contribution. So that's something that you have to clear. So we have the theorem. So that proves the theorem. Okay. These are all the remarks meaning or explorations I made. So that proves the theorem. It's nice to spend some time on these kind of things, exploring and understanding. Now we consider the following problem. Suppose we use an alpha, which is a step function. Finite jump discontinuities you have on the at points on the interval. Okay. So the next theorem is about this. Suppose Cn is greater than or equal to 0 for set, and these are non-negative numbers, and this is true. Let a sequence of points of distinct points maybe, and alpha x is defined as sigma let f be continuous on A. Then integral over alpha this is equal to sigma Now you see that this is an infinite series. In fact, you see that, so I'll just make a remark here before proving the theorem. a series sigma finest infinity is given. This may be expressed as an integral. Now this is quite simple. So you just gear it into this one. So choose the interval, an interval AB and points, sequence of points the sequence of points listen. Choose then what you get with the choice of alpha equal to sigma alpha n I x minus Sn. We then have integral a to b this is equal to sigma so this infinite series, the convergent infinite series can be expressed as an integral with an appropriate choice of alpha and a function f. This is the point. Or in other words, you are unifying the ideas of an infinite series with that of an integral. Okay, so it's a unification. Okay, so you are able to express any convergent infinite series as a Riemann series integral. Now this is one advantage. Okay, so that's something to do. So now we will give a proof. Sure. So let us work on the proof. Sigma Cn converges implies the series now this is because you see that I x minus Sn okay, for f dx. Okay, so either it is 0 or it is 1. That's what I have. Okay. Therefore, this is less than or equal to 1 for f dx. So we can use that, and then of course by the comparison test we can get this. The second, this two. So the second observation is that alpha x is monopole. In fact, it turns out to be, and alpha a equal to 0 and alpha b equal to sigma c infinity. So the points are all spread over there. In any case, we get a step function. Okay. So it is squeezed between these two numbers. Okay. Now this is quite easy to check. Okay. Let choose C such a sequence. Okay. Choose n such that summation from the tail of the series Cn is less than Cn, because it is given to be convergent, there are positive numbers, so that's assured. Now we split this one into two parts. Okay, so we write two parts. So we write alpha is. So let me just work out this. So put alpha 1x to be Cn and alpha 2x to be equal to both are monotone functions. Okay, then what you have is, this is something very easy to check. Then A to B This is equal to sigma this is exactly as we did in the previous case. Okay, right? So it just picks up FCN at those points and this is and what is. Now, if you take alpha 2a equal to 0 and alpha 2b equal to sigma I x minus xn. Therefore, this is equal to this one. Alpha 2b is put x equal to b there, and this is what it turns out to be. And you see that alpha 2b minus by our choice that we have made, this is less than x. Okay. And the consequence is that integral a to b f d alpha 2, this is bounded by m, where m is the bound for f on the interval a. Right? Therefore, m equal to so it's a bounded function that we have taken. Okay. Therefore, we have earlier proved that f d alpha 1 plus alpha 2 is equal to f d alpha 1 plus f d alpha 1. So we make use of that. Therefore, we have integral this is less than or equal to, because this becomes simply integral a to b f d alpha 2, and that we have estimated here. Okay. And what is this? This we already have. This is equal to, that is this is equal to 1 to n Cn S. This is less than or equal to, because these are equal. Okay. Now by letting then we have integral of a to b so one of the positive outcomes of the generalization of Riemann integration to Riemann series integral is that the infinite series also could be unified with the integration theory. Okay, so that's what you see in this result, right? Now, if you carefully analyze this integral if you analyze, what is it? There's a weight here. Okay, so it is the jump discontinuity that appears at the point S1 that is coming as a weight. So you have a weight there that multiplied by Fsn is the contribution to the area. So the contribution comes only from those points Sn, and this is what you have. Essentially, we are driving at the concept of a measure. Okay. So at the point Sn has a measure. Okay. Whereas you see that when you use this particular alpha, what is happening is that the measure or the weight is contributed exactly at this point, at these points S1, S2, etc., Sn. Nowhere else, and that the weight is consists of just Cn that you have. Okay, right? Now, if you look at this picture, it's very interesting. If you take the interval A, B, and then this is from alpha A to alpha B, because you are using a monotonic function. And what happens is that suppose there is a point S where there is a discontinuity, which is something positive. Okay. So apparently this particular interval, a degenerate interval, has a length, a positive length. Okay. So that is what happens when you have a jump. So we could use this idea to express a infinite series in the form of an integral. So that is the unification that you have obtained in this case. I think I will stop there and then continue with it in the next lecture. Thank you very much.